What's up everybody? My name is Eric. Welcome to my channel, Eric the Tutor. Welcome to my channel, Eric the Tutor. Today, we're going to be talking about nucleophilic acyl addition. But to start, I just wanted to review general structure when we're working with carbohydrates. What happens when we react a general carbohydrate with a base? So let's go ahead and show something that looks like this. When we react this with base, in previous videos we have shown the mechanism, so I won't go through it again. I just wanted to give a basic representation here. When we react this with base, we expect to get epimers of each other, so we expect to get the same exact molecule, and we also expect at C2 to get the epimer. So the this R configuration will have gone to S. So we should expect to see two different molecules there. We also expect to see the rearrangement. Now the rearrangement is when we ended up getting the ketose form at C2. So here is the ketose. Just like that. So that's our general structure. We can expect to see that anytime we react that with base. Now let's go ahead and jump into nucleophilic acyl addition. So I won't draw the whole reaction. I won't draw all of the parts because most of the stereocenters are staying the same. But let's go ahead and show the main parts, and we'll go through the reaction mechanism. So today we're going to be working with phenyl hydrazine. Phenyl hydrazine. So what does phenyl hydrazine look like? Well, we have our phenyl group, and then we have a nitrogen with a hydrogen coming off of it, and an NH2. So this is what we will be reacting our carbohydrate with. So let's say we had something that looked like this. I'll go ahead and put R down here for the rest of the carbohydrate, and we're going to be reacting this in H3O+. H3O+. So first step, let's go ahead and charge up that carbonyl. It's going to grab an H from the H3O+. We expect to get, here's that plus. Nothing changed down here. Now we expect to see, let's go ahead and involve our phenylhydrazine. So our phenylhydrazine, the lone pair here is going to come and grab the carbon, push this up, right? We knew that this strong base here was going to attack at this carbon because if we drew a resonance structure, we know at that particular carbon, the carbon would actually be positively charged. So much more electrophilic than anywhere else on this molecule. So let's go ahead and draw what we get. So here's our COH, and here's our nitrogen. Our nitrogen still has two hydrogens attached, and the rest of the molecule, NH, pH. And pH will stand for the phenyl group. Great. Let's go ahead and draw a little bit more just to be thorough here. So here's our R group. Now, what do you expect to happen? Well, in this step previously, way up here, we formed water. So now we know we're in a solution of water. So our water here can act as our base. We can do acid-base reaction to grab this hydrogen, use that bond to form a lone pair on the nitrogen. So let's go ahead and see what happens now. So there we formed H3O+, and we ended up getting carbon. Here's our OH, hydrogen. Here's our nitrogen with a new lone pair on it. Hydrogen coming off, and here's the rest, NHPH. Here's our OH and our R. So this lone pair here was just generated, and we just formed some H3O+ floating around. So now we have some H3O+ floating around. So what's going to happen? The O being very basic here, the alcohol group coming off of this carbon here, can use one of its lone pairs to go grab a hydrogen. we're going to form a good leaving group here. Now, we'll see exactly why we're forming that good leaving group in just a moment. So let's see. We have this hydrogen coming off the carbon, nitrogen with the hydrogen, and the rest of our NHPH. Here's our OH and the rest of our R group. Now we have a good leaving group. So this lone pair can form a double bond and kick this out. So what does that form? This is actually going to form something known as, this is our imine. This is imine formation. So this is one of our intermediates as we go through this reaction mechanism. So that water had left, water's gone. We have this carbon here. We have this carbon here with its hydrogen. Here's the nitrogen. Here's the rest of our group. We have our NHPH and the rest of the chain. OH and R. Wonderful. So now this nitrogen here still has a hydrogen coming off of it. So this is positively charged. We just lost some water, so this water can come make the nitrogen happy. Let's go ahead and make the nitrogen happy. So now we get HC double bond N with a lone pair, NHPH. Perfect. And all of these nitrogens we know have lone pairs on them, and the rest of our molecule, the rest of our carbohydrate. Awesome. So this is actually going to be our imine. Now, if we went and carried out this reaction with 2 more equivalents of phenylhydrazine, let's go ahead and do 2 more equivalents of NH. Let's go ahead and put NH2, NHPH. 2 more equivalents. Then we would expect to see this final product here. So let's go ahead and show what our final product would look like. We would expect to see C double bond N and HPH. Here's our hydrogen. Another C double bond N. So it went through the same reaction mechanism, but now we went through and hit the carbon next door to be able to do that. So in total, we used 3 equivalents of our phenylhydrazine. So here's our N, and here's our NHPH. NHPH got a little cut off there, and the rest of our molecule. So this OH, let's go ahead and see this OH here. This group ended up turning into a new NHPH. So we just have the R group coming off of here. If we had further groups, if we had more, if we had another OH coming off of here, then we would expect to see that OH right there. Now this phenylhydrazine is working at the electrophilic carbon way up here. So our electrophilic carbon and the carbon right next door. The carbon right next door. That is the reaction mechanism of the phenylhydrazine. Thanks, guys. See you next time.